Okay, here we go. Starting lesson 4.3, the last lesson in Unit 4. So what that means to us, the pattern that we've kind of set up is this is an even unit. So after this one, we are going to have a multiple choice assessment over units 1 to 4. So make sure if you haven't started preparing for that, probably be a pretty good idea to start doing so. And so the last thing that we're going to see actually gives us a chance to revisit limits, which would be very helpful, especially when you think about doing a cumulative exam over everything so far. And we're going to revisit limits and investigate something called L'Hopital's rule, which gives us a chance to use our knowledge of derivatives to help us with evaluating limits. And so let's look at a couple things that we're going to want to remember. And this will be some really good recall if you can draw back to these. There were a couple times where we had limits pop up where when we tried direct substitution, say like on limit as x goes to 0 of sine of x over x, that would have yielded 0 over 0. But in this case, the limit actually turned out to be equal to 1. But there was no manipulation we can do on that. There was nothing algebraic that we could do to prove that sine of x over x at that limit was equal to 1. It was just something that I would have asked you at that time to investigate on your calculator, something that looking at it graphically would have confirmed that this is our final answer. Same with something like the limit as x goes to 0 of 1 minus cosine x over x being equal to 0. This starts off as being an indeterminate form, but it turns out the limit does have a real value. But again, there was no manipulation we could do on a problem like that. So before getting into how we're going to deal with those problems and this idea of L'Hopital's rule, first let's just get ourselves a basic recap of limits. What we need to remember is when you evaluate limits, the first thing that we try to do is direct substitution. So like when I say the limit as x approaches 3, so I'm investigating what's going on with my function as x gets very close to 3 from either side, first thing we always try is to directly substitute that value. Because if the function is defined at that value, that is what your y value would approach. And in this case, we would get 1/3. As x approaches 3, my f of x values approach 1/3. But if we recall, the problems were not always that straightforward. For example, if you do the limit as x approaches 2 for x squared minus 7x, or 7 times 2, plus 10 over 2 minus 2, this gave us a situation where we had 0 over 0, or what we called the indeterminate form. But this one, unlike the two trig derivatives that we see up top, this one we could manipulate. We could, in this case, looking at a rational function, factor our problem. Factoring the numerator x minus 2 times x minus 5 over x minus 2. And we would have noticed, well, this actually shows we have a hole in the graph at 2. A hole in the graph means my limit can still exist. And evaluating at the simplified version, we got a limit equal to -3. But this is only doable, only possible due to factoring. What about when we run into problems where we can't factor and the manipulation is too complicated? Well, in those situations, we look to something called L'Hopital's rule, which tells us that if we are looking at the limit as x approaches c for f of x divided by g of x, something that we can write in a rational form, and we get the indeterminate form 0 over 0. Or even, we'll open ourselves to the possibility of infinity divided by infinity. What this means for us is that both f of c and g of c equal 0. Well, what L'Hopital's rule states is that we can apply the following. The limit as x goes to c of f of x over g of x will equal the limit as x goes to c of f prime of x over g prime of x. Now, one thing I want us to note is this is not the quotient rule. This is saying that if I differentiate the numerator and differentiate the denominator, those limits will match up exactly. And so what I want to do is I want to show a quick proof of this. If you are not interested in that, I will bring up a little card to tell you where you should fast forward to. But if you would like to see the proof for L'Hopital's rule and figure out why this is going to be true for the indeterminate form, please go ahead and keep watching. And so what I'm going to say is if you have the notes that I passed out from the class, the back of this sheet should be blank. If not, just get out a separate piece of paper or find space on this one. And what we're going to look at is the limit as x goes to c for f of x over g of x being equal to 0 over 0, which again was going to imply that f of c equals 0 and g of c equals 0. Well, how I'm going to prove L'Hopital's rule is I'm going to say that this limit will be the same as f of x minus 0 over g of x minus 0. I haven't changed the value because I'm just bringing zeros into the problem. But what that allows me to do is make a substitution. And those zeros, I'm going to swap out for these two function values. I know that 0 is the same as f of c, and I know that this 0 in the denominator I could replace with a g of c. So selective substitution in this case. Going one step further, I'm going to take advantage of the fact that if I'm dealing with a fraction, I can divide the numerator by whatever I want as long as I divide this expression in the denominator by the same thing. And what I'm going to use is x minus c in order to set up these two rational expressions in the numerator and denominator. Now at this point, you might be able to see what I'm going for. Recall that the limit as x approaches c for f of x minus f of c over x minus c, that was the limit definition for f prime at that c value. So using a property of limits, I can evaluate the limit for the numerator, limit as x approaches c of x minus f of c all over x minus c, over the limit as x approaches c for g of x minus g of c all over x minus c, which will become f prime of c over g prime of c. And moving back into a limit notation, that will equal the limit as x approaches c of f prime of x over g prime of x. And there is L'Hopital's rule. But the biggest thing to note is the entire reason why this was able to be set up was because we had this 0 over 0. Because of f of c equaling 0 and g of c equaling 0, I was able to make substitutions for these two values. This in general will not work if either f of c or g of c is defined as a value not equal to 0. So let's move back into our example problems. So picking up with this new rule, this L'Hopital's rule, we're going to evaluate each limit and use L'Hopital's when possible. The big thing is continue to try by direct substitution first. So in this case, trying to evaluate this limit as x approaches 2, for the x minus 2 in the numerator, we'll get 2 minus 2. 3 times 2 cubed minus 6 times 2 squared plus 2 minus 2. That will yield 0 over 0, which is my indeterminate form. So we're going to try this one by using L'Hopital's rule. I could try factoring, but especially with that cubic on the bottom, that might take a little bit more time. What I'm going to state is this will be the same as the limit as x approaches 2 for the derivative of the numerator, which is 1, over the derivative of the denominator, which is 9x squared minus 12x plus 1. Notice there's no longer going to be a 0 in the numerator. We're going to have a 1 over 9 times 2 squared minus 12 times 2 plus 1, which will give us 1 over 13. So let's try applying this in a situation where certainly we wouldn't be able to do anything like factoring or any sort of algebraic manipulation. The limit as x approaches 0 for sine of 6x over x. That is definitely going to be a 0 over 0 case, because you'd have sine of 0, which is 0. So we're going to try to apply L'Hopital's rule. Derivative of sine of 6x will be cosine of 6x times 6 all over 1. And this we will be able to evaluate, because we're going to have cosine of 0 times 6 over 1. Cosine of 0 equals 1. So 1 times 6 over 1 equal to 6. And notice that this just expands what we're able to do regarding limits. It allows us to, in situations where it looks like a limit is not possible, or in a situation where it looks like it'd be nearly impossible for us to work algebraically to solve a limit, L'Hopital's rule allows us to use our knowledge of derivatives to get rather quick solutions. And so moving on to our last example, first thing, notice in the first two examples, we applied L'Hopital's rule once. Got to one new setup that when we did direct substitution gave us our final answer, but on this last problem, something weird is going to happen. So limit as x goes to 0 of 1 minus cosine x, so 1 minus cosine of 0 over 0 squared. Well, that's going to be 1 minus 1 over 0, which will be my indeterminate form. So let's apply L'Hopital's rule. Limit as x goes to 0 of, well, derivative of 1 is gone. Derivative of negative cosine is going to be positive sine of x over the derivative of x squared, which is 2x. But that's going to yield sine of 0 over 2 times 0, which will still be my indeterminate form. The nice thing about L'Hopital's rule is it can be applied to the same problem more than once. You can keep applying it until you either get something that yields a real determined value or until you have enough evidence to say that this limit doesn't exist. So applying it one more time, this would be the same as the limit as x goes to 0 of derivative of sine of x is cosine of x, derivative of 2x is 2, and we'll get cosine of 0 over 2. Well, cosine of 0 is 1 over 2. We do have a determined value, and that 1/2 does represent our final limit. So the big things coming out of this section, again, it is a very specialized rule for dealing with certain types of limits. Limits that can be expressed rationally and yield our indeterminate form 0 over 0, or you'll see some examples in the practice where we could even operate with an infinity over infinity. And the other thing to remind yourself is this is not the quotient rule. Quotient rule is still what we use to find the derivative when we have two functions being divided. L'Hopital's rule says to take the derivative of each individual function and evaluate the limit using those two new functions. And so that ends Unit 4. Make sure you review and summarize this final section of notes. Move on to the practice when you are ready for it. And please make sure, if you have not done so already, that we are starting to study for the Unit 1 to 4 multiple choice. That means going back and reviewing everything that we have done to this point and making sure that we have a full grasp of all material that we have covered in the course up to right now. And that's all I have for you right now. So thank you for watching Lesson 4.3.